Okay, hello everybody. Let's get started, please. Before we begin, I have one quick announcement regarding the homework assignment. If you recall, when the assignment was given out, I showed you the test data that I gave you that you can use to test your code for homework 1. It was that it's a heap file, basically, right? That test.dat file that's in your repositories. Well, somehow, and I honestly have no idea how, an extra byte snuck into that file in the beginning, and usually 1 byte wouldn't be that big of a deal, except for it does throw off where everything appears in the heap file. Again, I'm really confused about how this happened, but that's not really important. The important thing is this post on Piazza, I did post a corrected version of test.dat. So if you want to grab a copy of that, erase the one that's in your repository, go find this Piazza post. Actually, I can pin it, so it's right up at the top, so it's easy to find. So sorry about that. I wish I knew what happened so that I could keep it from happening again, but at least we have a fixed file. Yes?
Okay, so if we were to take that file and copy and paste it onto the one here, could we commit that?
Sure.
I'm just trying to make sure I don't get merging that, introduce a new error like we can.
So I think you could commit it, but if you're worried about merge conflicts, then actually the better way to go about it would just be to resync your repository with my repository, because I also put this copy of the file in the base repository. So go to Bitbucket, do the sync operation, just like you had to do to get the unit tests. It's the exact same thing. Just go do a sync operation on the repository, and then that should take care of the problem as well. So you got 2 options on how to pick up that file. I have to be honest with you, I have not noticed a lot of errors on the tests, even with that additional byte in there. I imagine it's probably got to screw up some stuff, but I actually feel like the vast majority of the tests probably wouldn't notice that that byte was there. Mostly with reading, writing tuples is what I would expect might cause some problems, but the other stuff should work, even though that extra byte snuck into the header of the file. So I just want to make sure everybody was aware of it. Go out and make sure you grab a copy of that file in whatever way is easiest for you. And yeah, that's it. Any other questions before I hop into today's material about homework assignments or other stuff? So the assignments due 1 week from today. I actually saw people in my office hours yesterday who looked like they were done. That was great. Fantastic. If you're still working on it, you know, there's more office hours actually today and tomorrow and Sunday, I believe. So lots of opportunities to get help if you need it. If you haven't started on it yet, you probably want to do that soon. It's not a small assignment. It's not a short assignment. So please, please, please get started on that sooner rather than later. All right, if there aren't any questions, let's go ahead and hop into today's material. This is actually one of my favorite topics that we're going to cover all semester. I love this stuff. It's a lot of fun. Actually, I love everything that we do in this class for the most part, but this especially is one of my favorite topics, so I'm really excited about today. It is a bit on the theoretical side, but it's important to have a good theoretical background of these relational operations, because what I'm going to ask you to do on the next homework assignment, which is coming out next week, by the way, is implement these relational operations. Homework 2 is basically implementing the operations that I'm about to talk to you about today. So it's going to build a lot off of the concept of a relation that I introduced in class on Tuesday. So just real quick, as a review, before we get started, what's a relation? How would you define that? I'm sorry? Primary key and foreign key. All right, so let's be careful. That's a relationship between 2 tables. Yeah, I know. I can understand how you got there. What's a relation? A set of tuples. There you go. A set of tuples. A relation is a set of tuples. So we talked about this on Tuesday, right? Tables are relations, right? Tables are sets of tuples. They are relations. but not every relation is a table. And hopefully today, as we go through some of these operations, we'll make that very, very clear that there are lots and lots of relations that are not actually tables. So let's go ahead and start diving in. These are the SQL clauses that I've introduced to you so far, I believe. So what does select do in a SQL query? Yeah, set of columns. So what columns do I want to be returned? And then the from clause is what? Yeah, table or multiple tables, perhaps. All right, the where clause does what? Yeah.
Filters the results that you're going to get from select by some constraint.
Filters the results, usually filters out some rows, so I'm filtering out rows. And then order by, I think, is very obvious. It just sorts things, right? Group by is maybe the trickiest one that's up here. What's group by do for us? Go ahead.
It actually will return different relations to tables based on what I forgot what the technical name is for it, but you got to give it some sort of specification that like to split it up.
So group by is always used with another particular piece, which is called an aggregate. So if I'm doing min, max, average, sum, things like that, making aggregations, I can use group by to perform those aggregations not over the entire table, but based on some grouping condition, right? I'm bringing this all up because one of the things that I want to talk to you about today is how do these relational operations, the theoretical relational operations, match up with these concrete implementations from our queries. This is what we're going to talk about today. How do these things actually work? What are the operations that we need to perform in our database to accomplish these clauses, right? So let's begin. We're going to talk about relational algebra. Remember, a relation is a set of tuples. So really, these relational operations are just set operations, largely. There's several of them that I want to talk to you about today, some of which are far more common than others. You can see that some of them just require one set to operate on. Those are the unary operations. And then we have relational operations, which require two sets to operate on. So we're going to start with the unary operations first and just go down the list and talk about what they do. The first one on our list is select, and you might be thinking, okay, this is going to match up with the select clause. That's not true. That was a very poor name choice by, I don't know which one was first, the algebra or the SQL clause. I bet the algebra was first, and the SQL language, for whatever reason, also chose to use the word select, but for a totally different purpose, right? The relational algebra select gives us a condition to specify what tuples from a relation I want to keep. That's not what select does. What does that sound like to you? Which clause? Where? It's the where clause, right? So the select relational algebra operation equates to the where clause. And so here's what it looks like in algebra. We've got the Greek symbol there, followed by the condition, and then in parentheses. Now here, employees is a table. We've been using an employee database, right? But it doesn't have to be a table. It can be any relation. Any relation can go in the parentheses. It could be a table. A lot of times it will be a table. Could be any relation that goes in there. This is how we execute our where clause. This is how we represent our where clause using relational algebra. All right, so let's talk about this in a little bit more detail. The result set after computing this operation is going to have the same attributes as the one we started with, meaning all of the columns are left alone, right? I'm going to have the same number of columns that I started with. This operation does not affect the number of columns that I'm going to have in my results. It's also commutative. If I perform two selects in a row, and then I reverse the order, right? I end up in the same place regardless of which way I get there. The same place. I can reorder these select operations all day long and it's not going to affect the results. What's the bound on the number of tuples? So if a relation starts with n tuples, what's the upper bound on the number of tuples that I could get out of this relation? Yeah. N. Which would happen if... Go ahead.
Everything meets the condition.
If everything meets the condition, if the condition's broad enough to select every single tuple in the relation, I could have the entire relation pass through. Most of the time, that's not going to happen, but it could. It could. All right, that's the select operation. The next operation to talk about is the project operation. So for project, we use the capital Greek letter pi, followed by the names of columns that we want to keep. So any column that's on that list is going to be a column that we keep from the relation that's in the parentheses. Any columns that aren't on that list, we're going to chop off and throw away. So which SQL clause is this matching up with? Select. This is the one that matches up with select. Select goes with project. Okay? Duplicate tuples, so if I chop off columns, right, and the results now leave me with duplicates, duplicate tuples, those are going to be removed. Why? Think about how that could happen. How could this happen where I chop off some columns and then what I'm left with is a whole bunch of duplicate tuples? How could that happen? Yeah, in the back. Drop the primary key column, yeah. Or any column that's defining uniqueness across my tuples. Doesn't have to be the primary key column, right? If I project those columns off, then I'm likely, not guaranteed, but likely to have duplicates, duplicate tuples, which are then going to be removed. Why? Yeah.
Because like if it's simply good, the operator just simply sees that it's returning the same thing more than once. I mean, it's identical entry. You don't need it.
Don't need it? Well, there's a more, I guess, technical reason for why. What's a relation? It's a set. It's a set. We don't have duplicate things in sets. Sets don't have duplicates. This actually, though, is an area where the theory and the implementation of databases typically diverge. Right? Again, remember, in theory, relations are sets. We're doing lots of set operations on them. On an actual database, that actually isn't true. An actual database will keep all of the tuples, whether they're duplicates or not. You actually can see duplicate values in the relations on an actual database. Most of them, anyway, as far as I know. So this is an area where the theory and the implementation diverge. Yes?
So if I have a database and I want to clean my database and solve the redundancy, how can I know that if the database management system wouldn't show me the duplicate tuples?
Well, so I mean, the easiest thing to do would be to run a query and see what happens, right? Do I see duplicate tuples in the results or not? That will give you a clue as to what the database is actually doing. But then, to take that a step farther, let's say I want the database to behave more like the theory and remove any duplicates. There's a way to do that using a keyword, distinct. That pulls the implementation in line with what the theory says it's going to do. Great question. Any other questions? Yeah. Is it possible to remove the primary key? Sure. I can take off any column that I want. In fact, if you look at this particular example that I have here from the employees table, I'm pulling last name, first name, and salary. I don't think either of those columns are the primary key. So absolutely, you can project off the primary key. You can project off any column that you want. Yep. Let me just see if I can get the lights on real quick on the board. So you get, whoops, wrong way. Sorry. Okay, that's better. So you guys can actually see. Wow, that's really bright. All right. Yeah, whatever. What's the bound? If I have a relation of n tuples coming in, how many tuples am I going to get out? This is an easy one, I hope. Yeah, n. It'll always be n. I'm chopping off columns. I'm not chopping off rows, right? I'm not removing tuples. Unless duplicates get removed. That's the one case where I might have fewer tuples coming out than coming in. Is it commutative? If I run two projections back to back, and then switch the order, will I get the same result? What do we think? No? Why not?
Because like when you, like if the first time remove some instances, you may not have others that would have obtained if the second instance.
Okay, let's see. Let's think of an example, right? We have a projection here, keep last name, first name, and salary, and then let's say I wanted to have another projection that just keeps, I don't know, the primary key, maybe? Something like that, the employee number. So if I run this one first, followed by the second one, the primary key is not even on there anymore, right? We've already projected it off. So what will I end up with? I'll actually end up with nothing, because none of the columns that I wanted to keep are around anymore. Whereas if I switch the order, the primary key, I keep the primary key first and then say, all right, give me the last name, first name, and salary. What do I end up with? I also end up with nothing, right? And with no columns. Or if I take a more generous approach, let's say that I'm going to only project columns that do actually exist, right? And within the relation. Will I get to the same place? I think the answer is yes. I believe that I will. I believe project is commutative. Any questions before we move on to the next one? All right. This is, oh yeah, question. Switch the order, like the mathematical property, commutative. I can swap the order of operations and still get the same result, like addition. 2 plus 3 is 5, 3 plus 2 is also 5. So rename, all this does is apply a different name to a set of attributes on a relation. This is necessary in certain situations. We actually haven't talked about how to do this in SQL yet, but does anybody know how you would do this in SQL if you wanted to? Does anybody have enough SQL background to know? Yeah. As, yeah, it's the as keyword. I would say lname as last name. Right? This would rename the lname column, but it's not a permanent rename. It's a temporary rename, right? It's a renaming operation for the length of this particular query. As soon as the query is done executing and I see my results, the rename is done. It's gone. It's over. I'm not permanently renaming columns from a table. There actually is a way to permanently rename columns from a table, but that's less useful to us. This is more useful. Why might we want to do this? There's a very good reason. Yeah, in the back. A subquery, so a query within a query. We're actually not going to talk about that a ton, but you're absolutely right. That is when you might want to do it. There's another more straightforward reason, less complicated than a subquery. For convenience, if I just want to format the names a little bit so they look nicer on the results, sure. Or
you're trying to compare results from two tables and both of them have a column that's the same name.
Yeah, we have name conflicts or name overlaps across tables. That's exactly why. That's the most common reason, I think, to do something like that. We have name conflicts. This allows me to rename one of the columns so it's now clear which column I'm referring to in the query. Interestingly too, as doesn't just apply to columns. This rename operation only applies to columns. The way that it's written only applies to columns. But in SQL, I can apply as to table names as well in the from clause. I want to temporarily rename a table. And we may see that actually a little bit later on today. Okay. Any questions on that? So this does not change any of the data. This has no effect on the tuples. This has no effect on the number of columns. This is just renaming some columns for the sake of convenience. That's it. So that's all of the unary operations. What we're going to talk about next are the more set-oriented operations, starting with union. If you've taken set theory, seen any kind of set theory before, right? Union should be a familiar operation. It's a combination of two relations. All of the tuples in both relations combined together into one relation. Now there are some restrictions on what has to be true in order for a union operation to work. I have to have the same number of columns in both. And the data types of those columns also has to match. I think of it as a vertical alignment, actually. If I think of two relations or two tables or however you want to think about it, if I want to combine them together into one set, I'm taking one table and I'm sort of lining it up with the other table vertically, right? So that they share columns now. So the number of columns and the data types of those columns has to line up for me to be able to do that. This is not a very common operation in databases. It's pretty common in sets. We use it with sets all the time. You can do it on a database. In fact, here is the SQL code to perform a union. It's relatively straightforward. I write two queries. There's two queries, two select queries, and I just stick a union in the middle. So that'll join them up. But again, not a particularly common operation. Let's talk about intersection and difference, also set operations. So intersection is going to be all tuples that are in both relations. If I have a tuple that's only in R or only in S, that will not be included in the results. Only the tuples that are in both will be included in the results. The way we do that in SQL is with the intersect keyword. And then R minus S, set difference, is going to include all tuples that are in R but not in S. So what are the unique tuples that are in R, right? Is what we're looking at. Actually, both of these, it says difference is not often used. Intersection is not often used either, at least not in databases. Less often than even a union would be. And you might be wondering, well, then why the heck are we even talking about it? I'll explain why we're talking about it in just a little bit. But before we get there, let's talk about whether these are commutative or not. Can I swap the order of a union or an intersection and get the same result? Should be reviewed from set theory if you've taken it. See people nodding their heads, yes, you can. What about difference? No. Subtraction is not commutative. The order matters. The order definitely matters. Okay. All of that leads up to perhaps one of the most important operations that we're going to talk about today. Cartesian product. Cartesian product. It's going to combinatorially combine tuples from two relations. So think about Cartesian product has uses in mathematics, calculus, probably when you first saw Cartesian product, I would guess, right? It's the same idea here. I've got two sets of tuples. Let me draw a little example. Here I have columns A and B, right? 1, 2, 3, 4. As my rows, here I have columns C and D in the second relation. 5, 6, 7, 8. Just some very simple tables for the purposes of this example. It's going to make a Cartesian product. So my result, how many columns? Anybody know? 4. All of them. A, B, C, D. All 4. So I take this row and I combine it with this row. And then I take this row and I combine it with this row, right? And then I take this row and combine it with this row. And then this row and that row. It's a Cartesian product. It's a Cartesian product. So the number of attributes in the result is always going to be the number of attributes in the first relation plus the number of attributes in the second relation. All of them, right? All of them. The number of tuples in the result will be what? Yeah. All possible combinations of rows. All of them. Now, I'm claiming this is very important, but actually, a Cartesian product by itself has limited utility. We're not often going to see a Cartesian product used by itself. We're going to see a Cartesian product used with another relational operation. In fact, a relational operation that we've already discussed today. Yeah. Under what conditions is this a useful operation? Very few. Very few. There's something in our database, though. There's something that we talked about, especially on Tuesday of this week, that exists between two tables that can make these Cartesian products a lot more useful to us. Does anybody know what I'm getting at? There's something that exists between two tables in our database. Yeah. A relationship. A relationship. A one-to-many relationship most often, right? One-to-many relationship. So what I want to do, the vast majority of the time, is not just a blind Cartesian product. I want to do a Cartesian product with the relationship, the primary key, foreign key relationship as a filter on that Cartesian product, right? So I'm going to use a Cartesian product combined with a select. And be careful, I mean the relational algebra select, right? The select operation, not the SQL select. If I have a Cartesian product combined with a select operation, that's what we call a join. That is the definition of a join. So it's a join, really, to maybe simplify it even more, is a Cartesian product with a where clause kind of attached to it. You can see in this example, from employees join salaries on, and then this looks like a where clause kind of, right? This is the primary key, the employees, followed by the foreign key from the salaries table. And so instead of just blindly combining all of the rows, I need to change the numbers a little bit for this to work. Right now, if I tried to join these two tables, let's say A is the primary key and C is the foreign key. Right now, if I try to join these two tables, what would I get? Nothing. There's no matches. There's nothing that meets that condition. There's nothing. So if I change the numbers a little bit, I can actually have a more useful example, right? Maybe add another row down here. So the columns in our result are the same. That doesn't change. What's going to change is how I compute what rows get added to this set. So I look at the first value in the primary key column of this table, and I try to find a match in the foreign key column of this table, right? And I don't see one. So this row is just not going to show up anywhere in my result set. There's no matches. It's not going to show up. If I look at the 3, though, I see I've got 2 matches. So that one will show up twice. 3, 4, 3, 6, 3, 4, 3, 2. Or, yeah. That's how a join works. It's not just a plain, naive Cartesian product. It's a Cartesian product with an additional condition attached to it. Yes?
So I guess that implies that Cartesian products are also commutative, because obviously if you flip those around with the C first, you would have got the same result.
I was going to ask that question next. Yeah, I mean, so there's a couple things we can talk about. If I swap the order of the tables here, does it matter? If I say not employees join salaries, but salaries join employees and leave the condition alone, does anything change? Nope. And then I can talk about the condition too, right? Leave the tables alone, but then talk about salaries equals employees, dot employee number. Does that change the results? No. No. The order that I specify the tables, the order that I specify the condition, does not affect the results. I get the same results back. So yes, it is commutative in that sense. Yep. It certainly is. Now, that being said, we'll talk about this maybe not next week, but the week after, I think. It does have an effect on performance. It does have an effect on performance. The order that I join tables does make a difference in terms of how fast I can perform that operation. We'll talk about that a little bit later, though. Yeah?
So what's the difference between this query and if I said select the attributes from employees and salaries, where employee that number equals salaries?
So you're suggesting that we just take this clause and put it in the take this value and put it in the where clause? Is that, am I understanding that?
Yeah, but without using. So what's the difference between using join and using
the where clause? Yeah. So the way you described moving this condition into the where clause is actually the old style. That's how people used to do it. That used to be how you'd perform joins. That was how joins were made. This join keyword it's not new. It's been around for a while, but it's newer than some of the other stuff in SQL. And so it is now the preferred way of writing joins. They'll both get you the same result. If I put this in the where clause, I'll get the same result back. It's just another way of writing the same query.
Is there any difference in performance?
Is there any difference in performance? That's a good question. I'm actually not entirely sure about that. I would, if I had to make an educated guess, I would say they would be very similar. If there was a difference in performance, it would be small. But I'm not 100% certain on that. That's a good question. What I do know is that I very much prefer this syntax because it keeps everything related to my join in one place instead of taking the condition and splitting it off and putting it in a different part of the query. So I prefer this syntax, even though the other syntax, the other way of doing it also works. I think this is a nice improvement. That even just that word join, right? Your eyes just sort of naturally gravitate to that, and so it helps your interpretation of the query. I prefer it from a readability perspective, code understanding perspective. So, we're not limited to just 2 tables. I can join multiple tables if I want to, and I would just chain joins together. So if I had another join that I wanted to perform, then I could say join another table. This column equals this column. And notice too, right, the columns that I used in my condition are a primary key, foreign key relationship. 99% of the time, those are the columns that you're going to be using there. In practice, the database actually does not care what columns you use in that condition as long as the data types match. Does not care one bit. I can put any 2 columns I want there, but it is very, very, very rare to see columns that are not part of a primary key, foreign key relationship in that condition. That's what the relationships are for, right? So use them. Use them. Are there any questions about this? Any questions? We'll see some more examples in a little bit. For sure. All right. So there's another kind of join to talk about as well called an outer join. So in this particular example, I performed an inner join, right? This table joined with this table. If I performed an outer join, there's actually three kinds, technically kind of only two, but three kinds of outer joins to consider. An outer join basically says, if I do a left outer join, for example, left literally means look at the table that's listed on the left side of the join, and I'm going to keep all rows from that table, whether they match the condition or not. But for the table on the right, I'm only going to keep rows that match the condition. That's it. So if I did a left join on this particular example, what that would mean is that even though this row doesn't actually have a matching row in this table, I'm going to keep it anyway in my results set. But now the question is, what goes here and here? Anybody have any ideas? Null. It's just nulled out. This result now is a left join between these two tables. I keep all rows from the table on the left and just put null in for the spots that I can't fill normally. A right join then would be keep all rows from this table, whether they match the condition or not, right? Same idea. And then a full outer join is keep all rows from all tables, from both of them, and fill in nulls when you don't actually have a match, right? Why would I want to do this? How is this useful to me? Yeah.
Well, for the last one, the full, like let's say that you got that you have like two tables that like you have like a new table like for 1 year, like you're collecting some data on some like students or employees like that. You have from 1 year and have another year, and then you realize, well, I don't want them in two different spaces. I want to put them all together. So you would do that, and then I guess you would fill in pertinent information.
So combining two sets together, I mean, that sounds more like a union to me than a join, perhaps, but maybe. I think an outer join, really what it does is it lets you see, it really clearly lets you see what values don't have a match. So if I'm interested in knowing, I'm trying to think, so if we use the employees example, right? If this is the employees table and this is a salaries table, this would let me see employees that don't have a recorded salary in the system, which would seem unusual, right? But maybe that's what I'm looking for. I'm looking for weird defects like that. I'm trying to figure out, is there any employee that doesn't currently have a salary listed?
So,
yes?
I'm searching for missing data.
That's one use case that it could be for, missing data, sure. It doesn't have to necessarily be missing data, though. It could be other, you know, it's all based on context, right? Maybe I've got a list of courses and students, and I want to see what enrollment figures are like. I could use an outer join to show me which courses don't have any students enrolled necessarily, right? Because they would just show up as nulls. As another example. Now I mentioned before, there's really only two outer joins that are used in practice. The right outer join is almost never used. If you really want to do a right outer join, what do? You flip the order of the tables and you use a left join. That's just a convention. There's no rule. There's no like the database doesn't care, right? It's people that care. If you write a join that uses a right outer join, it's not going to break anything. The database isn't going to mind. Your coworkers are going to look at you a little funny. They're going to be like, why don't you use a left join here, right? So left joins and outer joins are the ones that you're going to see most often. Any questions about that? Now I want to say, that being said, the normal joins, which actually are called inner joins, these kinds of joins, are by far the most common kinds of joins that we're going to deal with, that you're going to run into. Outer joins, though, are not uncommon by any means. They're still used with somewhat frequency, but the inner joins are the ones that are most common. All right, we've gone through a bunch of operations, and actually there are 6 in particular. The unary operations, select and project, and then the relational operations, union, difference, well, rename is also unary, I guess, and Cartesian product. These are what we call a complete set. And what I mean by that is that any operation that I want to perform on relations can be expressed using just those 6. Notice there's one glaring omission from that list. Intersection is not on that list. Intersection is not strictly required to be implemented. It is a lot of times for convenience sake, but I can write intersection as a function of these other operations. This is actually a classic set theory question that some of you may have seen, right? And when you took set theory, if you took set theory, but I can define intersection in terms of the others. Difference and union are all I need to define intersection, as one example. And so what this really means for us, right, is if we understand these 6 operations that are listed up here, I can execute any SQL query that I can gets thrown at you. That's actually a little bit misleading. It's a little bit misleading because one of the things that database manufacturers do is they like to add on extensions. They like to add on additional keywords, additional functions, additional functionality that falls outside of the basic set theory set of operations that can be performed. And so that's sort of in a different category. But if we're just sticking with the basics, right, the basic SQL queries, the basic select queries that we've been talking about so far in class, they can all be computed using the 6 operations that you see there. In fact, select, project, Cartesian product, and rename are the ones that we're going to be using the most. We're not even going to see union and difference pop up that much for our purposes. All right, so let's talk about something else real quick before we move on to another example. Earlier in class, actually the very first thing in class I showed you were those SQL clauses, select, from, where, order by, and group by. My question to you now is this: what order do these get executed in? I can use all of these in one query if I want to, right? What order do they get executed in? Which clause am I going to execute first? Is it select? No. Would I be asking you that question if it was? Maybe. Maybe. It's not select. That's not the clause that I'm going to identify first. Why? What am I going to do first? Yeah. Find the table first. From. This is number 1. The column names mean nothing to me until I have the table, right? The column names don't have any meaning unless I know what table they're coming from. So from happens first, which sounds a little interesting, right? But it's true. Anybody know what happens next? Yeah. Where? Good guess. Or maybe it wasn't a guess. I shouldn't assume that it was. Good answer. Why where? Why would I do where next? Yeah.
To decide what you're going to filter resulting by table.
I could do that any time, though, right? What's the advantage of doing it now?
Because you haven't actually tried to query the table.
I haven't actually tried to query the table yet. Well, I have to query the table to figure out if values match the condition or not, right? I have to access the data to do that. What's the advantage of doing it this early? Yeah.
You don't have to select all tuples in the table.
I'm sorry?
You don't have to select all tuples in the table.
I don't have to worry about it's getting rid of information as soon as possible, right? It's performance. If I filter out rows, that's fewer rows that I have to worry about messing with for the other stuff. Right? So where is going to happen pretty darn early in execution. As early as we possibly can. Mostly for performance reasons. All right, what's next? Select. Any other votes? I didn't mean to scare you. You're actually right. Select is next. Now that I've whittled out as many rows as I can, I've filtered out as many rows as I can start chopping off columns. For a similar reason, right? If the sooner I chop off the columns that I don't need, that reduces the size of my data set, which is going to make future operations faster. If I have aggregations, right, in this, average, min, max, things like that, that's going to help even more because that really condenses the size of the relation, the data set that I'm working with. What's next? GroupBy. GroupBy has to happen after select, or actually this is where things get a little gray, I guess. Some GroupBy and select, if I have an aggregate involved, they sort of go hand in hand. So they're almost simultaneous in that regard. They sort of belong together if I'm doing a GroupBy. So 3/4 kind of for those two, depending on whether I'm doing aggregations or not. And then that leaves order by to happen last. And think about it, sorting, right? Not the cheapest operation in the world. The more I can reduce that data set down, get data out of there, the faster that sorting operation is going to be. So in general, I don't want to say this is true for every single query that you ever write, but in general, this is a typical order of operations for query execution. There are always exceptions, and those exceptions are typically going to be made for performance reasons. If we think we can get away with doing something faster by switching the order around, we will. We will. But in general, this is a nice balance of getting us the performance that we want. Gets us the performance that we want, achieves execution goals as well. So all of that being said, what I'm trying to build up to here now is, recall that select matches up with which relational operation? Project. From, did that have a, that didn't actually have an operation associated with it, right? Not yet. Where was which one? Select. Order by also didn't really have one. GroupBy didn't really have one, right? I'm trying to get you to think about, though, if I give you a query, ask you to actually query some tables in the database, which relational operations am I going to be interested in first? And so you see select is here. From, actually what I might see in the from clause would be a join, so a Cartesian product. Maybe. Not required for there to be a join, but maybe. And joins actually make this order even more complicated. We'll see some examples of that as we go along too. Let's clean up some of these missing pieces here. GroupBy can be done. The way that it's specified using relational algebra is with a function. So that big fancy letter F just means function. There are actually lots of functions at our disposal on typical database implementation, GroupBy being one of the more common ones. So what we're saying here is, give me the average salary as a function, right, of all the salaries in the salary table. If I want to, so that's just a regular aggregate without a group by. If I want to do one with a group by, then I'll stick the group by column on the left side of the function. So this is what am I grouping by, and then the other subscript is what's the aggregate that I'm computing. You see the quotes there. It's technically outside the realm of relational algebra, but we like to talk about it. We'd like to talk about group by, so we came up with a way of including it in our relational algebra expressions. So what we've been building up to is this idea of a query tree. If I give you a SQL query, what do we have to do? First thing we have to do is understand what that query is saying, right? I have to examine that query and break it down into its component parts. That's actually Tuesday. Tuesday we're going to talk about SQL, the language, in a lot of detail. A lot of detail. So I get the query coming in, I have to break it down into its component parts, and then I have to figure out which relational operations are going to satisfy the different pieces and execute those relational operations in the proper order. We use a query tree to represent this. What operations need to be performed? What order do those operations need to be performed in? This is an actual data structure that your database implementation will create to represent the query, to bridge the gap between the SQL query and the relational operations that need to be performed. So let's take a look at an example of a query tree. We'll start with a pretty simple example, maybe work our way up to some more complicated ones. I want to know the names of all the employees and the salaries that they're making. I think I included the ER diagram so we could use it as a reference when we're solving this problem, right? So if I want to construct a query tree, first thing I'm going to do, remember we're looking at the from clause first. So I need to know what tables, right? In fact, actually we could go a step farther and write out the actual query if we wanted to. Maybe we should do that first. I want to know employee names and their salaries. So I know I need a select and a from. These two clauses are non-optional, right? I have to have those. Actually, I like to follow the order of operations and do the from clause first. So what tables do I need to make this happen? Employees and salaries. That's more than one table, so I know I'm going to need a join. I definitely need a join. That's okay. If I look at this diagram, I see there's a relationship between those two tables. So doing a join between them is a perfectly acceptable thing to do. So from employees, join salaries. And I now have to specify the join condition. The join condition is going to be based off of the primary key, foreign key relationship. So the primary key, you see the relationship. It's a one-to-many relationship. One employee has many salaries because people get promoted and earn more money over their careers, hopefully. So one employee, I would expect to see a foreign key into the employees table and the salaries table, and I do. I see employee number shows up in both tables. So that's my join condition. It's actually the same condition we saw on that example a few slides back, right? Okay. So I finished the from clause. It has a join in it. The other thing I need is the select clause. Do I need a where clause for this if I just want to know the last names and the salaries? Not necessarily. Not necessarily. I think all I need for this example is select and from. So I just need to decide what columns I want to select now. I see employees has first name and last name, so I'll include those. And then from the salaries table, I want to pull the salary column. Okay? So far, so good. This is the query that answers the question that I asked. What's the first name and last name and salary of all the employees? But we want to construct a query tree for this. So we want to take this query and describe it in relational operations, relational algebra. So let's do that next. I wish I had more board space for this. Let's see. Let's see if I can fit it over here so that I can leave this diagram up. I'm going to tackle the query tree in the same order of operations. From clause happens first. So my tables are going to be the first thing that get added to the tree. The tables are employees and salaries, and the way I represent those in the tree, they actually go at the bottom. They go at the bottom of the tree. Draw a big circle, I'll put employees. And I'll put salary. Or salaries. It's the name of the table. So there's my from clause, but I need to include the join as well. So how are joins expressed using relational algebra? What's that look like? It's a Cartesian product combined with a select operation. Cartesian product combined with a select operation. That's how I would expect it to show up in the tree. I have to join these two tables together with a Cartesian product. That's the x, Cartesian product. But I also need the select operation. So once that Cartesian product goes through, I'll write the select operation, which is based on the condition okay? I've got two operations, Cartesian product and then the select operation. That satisfies my from clause. I don't actually have a where to worry about. I do have a select, though, which I just erased it, but the relational operation for that clause is the project operation, which is a capital pi. So I'm going to have one more node in this tree, capital pi, that says which columns I want to keep. First name, last name, and salary. And here it is. This is the query tree for this particular query. We read it from the bottom up. I start with the tables, and I read it up the tree. We tried to match the order of operations. Now, actually, though, in practice, we don't necessarily have to construct our tree obeying this set of order of operations specifically, because what we're going to talk about in a couple weeks is actually optimization of queries. So what optimization does is it takes a query tree and then it reorders these operations based on a set of rules to give me the best performance possible, or to at least attempt to improve the performance of the query. And so that really ends up getting us back towards these order of operations. So, I mean, what I'm really getting at is, right, I could, for example, swap the order of the project and the where, and it would still be a perfectly valid query tree that would get me the result, right? There would be nothing wrong with that query tree. It wouldn't be an optimal query tree, but it would be a perfectly acceptable query tree that executes this query. And again, this is your task for homework 2. I'm going to ask you to take in SQL queries, figure out which relational operations need to be applied to execute that query, and then perform those relational operations. You're going to implement the relational operations that we talked about today. It's part of homework 2, starting next week. Are there any questions about what we did up here? Okay. So all day today we've been talking about relational algebra. There's actually another concept worth talking about called relational calculus. It's a little bit different. So relational algebra is procedural. I apply the operations one after the other, right? I apply a projection, then I apply a selection, then I apply a Cartesian product, right? Whatever order I need them to occur in. It's a procedural way of approaching execution. But the queries are not written like that. If I look at a SQL query, right, it's not written with the relational operations in mind. The query really, what it does is it defines a set of conditions, a set of boundaries that explains the data set. It defines a data set, really, at the end of the day, that I'm looking for. And that information gets turned into a set of relational operations that can be performed on a query. Think about why that is. Why don't queries just specify relational operations directly? Yeah. So it does allow for optimization. If I just had users write the relational operations directly, that assumes that they would know how to do it. I think that's actually more difficult. And that it also assumes that they would know how to do it in a performance efficient way, which I think is way outside the realm of, expectations for our users. I can expect people to tell me what data they want in the form of a SQL query. This is relational calculus. The SQL language is a form of relational calculus. That relational calculus statement then gets turned into a set of relational operations, which is very easy for the computer to understand and perform step by step by step. So this is the SQL language. This relational calculus idea is something for humans. It makes it easier for humans to describe the data set that they want. That's actually why SQL feels so much different from other programming languages that you've seen, right? As programmers, we're actually very used to writing things in a procedural way. We do it all the time. That's how a lot of other programming languages are structured. That's not how SQL is structured. SQL uses relational calculus for its queries that gets translated into relational algebra. Right? And so then, when I say no order of operations here, what I really mean is that it's not apparent from reading a query what the order of operations are. Most people would assume that this is the first thing, this is the second thing, this is the third thing, and that's not true. That's not how it's actually operated on. And so there's two ways of defining relational calculus. There's tuple calculus and there's domain calculus. So you can see that these queries both express more or less the same query. I'm looking for the first name of all employees with a birth date after 1960, right? That's tuple calculus, where T is defined as any tuple that exists in the employee relation. So T, give me the first name of all the tuples from the employee relation that have a birth date after 1960. This is a more or less equivalent query written in what's called domain calculus, which is a slightly different way of going about it. Basically, we're saying which variables we care about and which ones we don't really care about. So here, when I say there exists RST, you'll notice that the way I've defined a tuple is a lot more explicit. I've defined a tuple as all of the columns. RSTUV are the columns from the employee table. I'm basically saying I don't care what R is, I don't care what S is, I don't care what T is, as long as they exist, they're not null, I want to know what those values are. I want R, which must be the birth date column, to be greater than 1960. And I want the result set to contain columns U and V, which would probably be first name and last name. This backwards E stands for there exists. Basically means I want you to make sure this value exists. There's another quantifier called the universal quantifier, upside down A, which means every single tuple in the relation has to conform to this condition. We're not going to spend a lot of time talking about tuple calculus and domain calculus. Not today, at least. Not today. I just wanted to introduce this concept to you very briefly as an example to show that this is the theoretical side to how SQL queries are written. I actually think it's more valuable for us to not mess with the theory so much for relational calculus and just deal directly with SQL, the language, which is what I plan to do in class on Tuesday. So I'm not going to spend a ton of time talking about relational calculus, and I'll go ahead and say it because I get questions about it every semester. You're not going to see relational calculus show up on the exam, so don't freak out about it. I've literally spent 2 minutes talking about it, and we're never going to see it again. So not in this class anyway. Maybe a very small amount on Tuesday. All right, any questions before we end today with some practice problems? Any questions? We should have time to do at least one practice problem. We got 10 minutes left. Should be able to do at least one practice. All right. Write a query to show the names and birthdays of all employees, and I want to know which relational operations you used. Then I want you to write the query using relational algebra. That could take actually one of two forms. A query tree is fine. In fact, a query tree is most often what I prefer, but it's also valid in relational algebra to just, specify it almost as a algebraic expression where I can say pi and then have a projection, right? And then have a Cartesian product, right? This is also a valid relational algebra expression, just nesting the operations inside of each other. I think a query tree is a little bit easier to read and understand, but you're welcome to approach this problem however you like. This practice problem, I think, is maybe even easier than the example that we did. So if you're looking for a challenge, this one is pretty tricky in terms of constructing the query tree. But for the sake of time, we'll do the easy one for now, and maybe if we have time on Tuesday, we can do the harder one in class as well. I'm going to give you 5 minutes, and 5 minutes from now, I'm going to do two things. I'm going to write the query for this, the SQL query, the code, and then I'm going to turn it into a query tree to wrap up the day. So take 5 minutes, see if you can do those things real quick, and then we'll talk about it. All right, you know what? This one is actually so straightforward. I'm not sure we even need 5 minutes to work on it. What's the query going to look like? Select first name, last name, and birth date from employees. So what relational operations were used? Project. That's it. That's it. So the query tree is going to be relatively straightforward. Got my employee table down here, and then I've got a projection on these 3 columns, right? That's it. That one is very straightforward. What I'd like to do, since we still have a little bit of time left, I don't think we'll have time to do all of this, but let's write the query. Let's write the query for this, and then you can work on the query tree as a little bit of practice before class next week. So let's write the SQL query for this. I want to see who the managers are of each employee in the database. I'm going to pull up the ER diagram because I think that's going to help us figure this out. So here's the ER diagram. I gave you the hints that we're going to need a join, and we're probably actually going to need a join on more than 2 tables. It's going to be multiple tables, right? So what tables do we need? Employees, department manager, that dictates who's the manager of departments, right? What other tables? Department employee, why? You're right. You're actually correct, yeah.
Managers are in charge of departments, and departments have employees.
Yep, managers are in charge of departments, departments have employees. That's correct. And you can see that I have a relationship between those 3 tables. I have a relationship between those 3 tables. So if I know who's a manager of a particular department, and I can match that same department with an employee, right? Then I should be able to specify the managers and employees. All right, this is actually a little bit tricky, but let's see if we can figure it out. I like to start with the from clause. I've identified 3 tables that I'm interested in joining together. And we can actually join them in any order. The order that we join these tables is irrelevant to the outcome, at least in terms of functionality. So let's just get these tables joined together. We'll start with employees. So what's the relationship between employees and department employee, the one at the top? What's the relationship? Well, what are the columns that I'm interested in? Employee number. On. What am I looking for? On employee number. Equals department dot emp number. Okay, so I've joined those 2 tables together. How would I join this other one at the bottom then? So I need the join keyword, right? What are the columns? It's actually not department number, it's employee number again. Employee number is the column that's shared between the employees table and the department manager table. So it's employee number again. So I would specify that. department manager dot employee number. So I think we're good on the joins for now. I've got all three tables joined together. So think about what we've got right now. Right now, if I just look at this query as is, I know it's incomplete, right? If I just look at this query as is, I've constructed a giant relation with all of the columns from those three tables, right, joined together based on the employee numbers that appear in those three tables. Now, what has to be true in order for me to know that somebody is a manager of somebody else? What has to be true? Yeah.
They have to be in the department manager table.
Uh-huh. That's true. There's another piece of information that's necessary. I want to know, how do I, what I'm really trying to get at is there's a relationship between managers and their employees, but it's not a relationship that I see on the diagram. It's a relationship that we need to reason about and figure out how to make. It's based on the department number. If I see the department number of somebody here, right, and I see the same department number show up for an employee, I know that they're the manager then of that particular employee. So I'm looking for department numbers in this table that match department numbers in the table up top. Does that make sense? Yes? Okay. So in order to, that's not a join though. That's not a join that I can necessarily do. I've already joined these three tables together, but there's no relationship between this table and the department employees table, right? There's no relationship there. So if I want to specify that relationship, what I really need is a where clause. Where department employee dot equals department manager. I think it's important that this goes in the where clause and not with the rest of the joins, because this is not part of a relationship. This is just a condition that we are specifying to solve this problem, to answer this question, right? Yes?
So is it not part of a relationship because you can't like grab something from the department manager?
I don't see a relationship drawn between the two. Yeah. And so then the last part that we need, I know we're just about out of time, but we're almost done. The last part we need is what? Names, right? I need the names of the managers and the names of the employees in the select clause. That's a little bit tricky though, because they're both coming from the employees table, correct? They could be. They could be. That's a little bit of a wrinkle. Unfortunately, I'm out of time, so I'm going to leave that as a thought process for you. Ask on Piazza if you would like over the weekend. I'd be happy to talk to you about it. If we have time in class on Tuesday, maybe we'll talk about it. But I'm out of time right now, so I will see you next week. Have a great weekend.